Hello, this is a presentation for the International Conference on Techniques, Technologies and Education. I am AlexAndonov, a PhD student from the University of Veliku Turnov. The topic is Mathematical Hyperoperations, and the title of the paper is Constructing a Hyperoperation Sequence, Pisa Hyperoperations. Our context is operation sequences, and a new sequence of operations will be constructed. When reviewing its properties, we stumble upon the sibling numbers. Two theorems are proven in the paper. The first theorem helps us decompose one Pisa expression into two or more. The second helps us decompose a tetrational operation into a Pisa operation and a tetration. We will start with notation used for representing operations. Operation sequences give us the context for the Pisa operations. After discussing sibling numbers and the two theorems with the Pisa operations, other aspects could be reviewed, like tetrational heights, areas of domination, and what happens when increasing Pisa level. We will put operations in angle brackets, which is useful with equalities. With inequalities, we have to use a sign if we have one assigned, or to use functional representation. The first argument of the operation is called base, and the second height. The third is level, and this usually shows the place of the operation in the sequence. The result, or the dependent variable, is not an argument, but is linked to the other arguments by the operation. The operation sequences are constructed quite the same way as the number sequences. We have an initial operation and a recursive rule, which allows us to define the next operation on the basis of the previous one. The hyperoperation sequence starts with addition, multiplication, and exponentiation. The level 4 operation is interesting. Tetration is not so well defined for non-integer heights. This is a hot problem, in a way analogous to the expanding of the factorial function to non-integer arguments. Commutative operations were put forward by Albert Bennett a century ago. What is interesting is for all operations, their arguments commute. The lower hyperoperations are constructed by applying operations left associatively. With big arguments, they grow slower than the hyperoperations. The Pisa operations are defined by the initial operation, multiplication, and by the recursive rule, in which the previous operation result is raised as a power to receive the new operation. The sequence can be extended in the opposite direction by taking logarithm of the previous operation. All operations can be combined in one function with 3 arguments. Thus constructed, the sequence includes multiplication, exponentiation, and lower 4 or chat. In the opposite direction, we can find Pisa summation as level 1, preceding multiplication. This drawing shows the motivation behind naming the sequence. The little circles are the bases. The height is the little figure on the top. The walls represent the level, and the result is I haven't figured it out yet. These are properties valid for all integer levels, which are easy to prove by induction. It is easy to imagine that they will hold for real and even for complex levels. This is an example of a Pisa operation. The fourth level of Pisa is chat. Here the result of chat is plotted against the base argument with different heights. Here the result of chat is plotted against the heights argument with different bases. The sibling numbers combined with Pisa operations have special properties, some of which are listed here. These properties hold for any Pisa operation with any integer level, and it can be conjectured the properties will hold with real and even complex levels of Pisa. The siblings are pairs of numbers which can be calculated by setting the arguments of the generating functions to a generating number a. There is only one pair of integer siblings, 2 and 4. Every Pisa operation can be broken into 2 or more nested Pisa operations. The sum of the levels of the result operations exceeds the level of the original operation by 2. The second operation is divided by the first argument, the base, and nested as the second argument of the first operation. When arguments of Pisa are within domains, the following equations are identities, one written in operational and the other in functional form. It can be conjectured that the theorem will hold for real and complex levels. Every small base tetration operation can be broken into nested Pisa and tetration. The sum of the levels of the result operation exceeds the level of the original operation by 2. The tetration is divided by the first argument, the base, and nested as a second argument of the Pisa operation. For every base, height, and level in domains, the equalities here are identities. It can be conjectured that the domains of the arguments can be extended. Tetrational heights of Pisa are such values of the second argument that can transform a Pisa operation with integer level into a tetration with integer height. If the value of the height of a Pisa operation is not in the tetrational height set, then the result is not a tetration with integer height. Here we compare the values of two Pisa operations, multiplication and exponentiation. The area of domination of multiplication is that part of the domains where the result is bigger than the result of exponentiation. The limits between the areas of domination of the two operations are given by these lines. What is interesting is that these are the lines and the areas between any two different Pisa operations. Thus, they are invariant of the level and are a feature of the Pisa sequence. Examining the Pisa results when the base and the heights are fixed and we are increasing the level, we find the values approach one of two fixed points dependent on base. Which of them is attracting point depends on the height value. Any questions? Any comments?